So how do we add floating point numbers? This is actually a lot harder process than adding 2's complement or unsigned binary numbers. So we actually have to extract the fields, basically, put the number back together, perform the operation, and then, break it back up into its fields. So here are the steps: extract the exponent and fraction bits, prepend the leading one, compare the exponents. If they're the same, we don't have to do anything. But if they're different, we're going to shift the smaller mantissa to the right, and then we're going to add the mantissas. Normalize the mantissa. We could get something where we get a 1 0 dot, 1 0 point, blah, blah, blah. So we have to shift it again and adjust the exponent. And finally, we might have to round the result if we ended up with too many bits of precision, and then assemble it back into the floating point format. So let's show an example of this. So let's add the following floating point numbers. So the first step is to extract the fields, the exponent and fraction bits. So we're going to have 3 F C 0 and then a bunch of zeros, and 4 0 5 0 and a bunch of zeros. And we're going to break up into the fields. So we have our sign bit. There's our sign bit. We have our, you have to be careful here because it goes across our hex digits. We have our exponent, our biased exponent field. And then we have the rest, which is our fraction field. And so the first number is, well, the sign we're doing this for positive numbers. We have our sign bit of 0, so they're both positive. The exponent is, for the top number, is 127, and the bottom number is 128. And our fraction bits are 0.1 for this top number, 0.1, bunch of zeros, and this one is 0.101. Okay, so we've extracted our fraction and exponent bits, and now we're going to prepend the leading one, right? It's implicit, but it's not unimportant, right? So we still need to, it's in fact the most significant bit, so we prepend that leading one to form the entire mantissa. And now we're going to compare the exponents. So one of the numbers had an exponent of 127, the other one of 128. So we need to shift, if we go back to our numbers, we had 1.1 times 2 to the 127 and 1.101 times 2 to the 128. And so, well, which one are we going to shift? If you have to shift something, this is the smaller number, right? N1, this number, we'll call this N1, and this one N2. N1 is smaller, right? It has the smaller exponent. And so we're going to shift that to the right by 1 bit so that we can make their exponents equal. And so we're going to shift N1 to the right. We get 0.11 times 2 to the 128. This is N1, and we still have N2 here. And so now we're going to add those mantissas. And we can, in this case, it looks like we shifted it back down to, or it took away the bias, but we don't necessarily have to. We could just leave that as 128. Right? They're relatively the same. And we're going to add these mantissas. So they have the same exponent. We can add them, and we're going to get 1 plus 0 is 1, 1 plus 1 is 0, carry the 1. We get 1 plus 0 plus 1 is 0, carry the 1, and we get a 1. And so we get 1, 0 0.011 times 2 to the 1, or if we just leave it as biased, which we can, of 2 to the 128. Unless we want to actually know the number. If we're trying to like print out the number at that point, we need to take the bias off, or we get some huge number when we were expecting something with the power of 1. Okay, so we added those mantissas, and now we're going to normalize it. So we need to have our binary point to the right of the most significant one, and so I'm going to go ahead and leave this as 128. 128. Result is not 128, but we'll leave that as 128 and see what happens here. We have 128. And we're going to float that binary point to the left by 1 bit. We're going to get 1.0011 times 2 to the now 129, or unbiased 2 to the 2. And we don't need to round the result. Clearly, this fraction fits, more than fits, in 23 bits. And now we're going to assemble it back into the floating point format. So we left it as biased the entire time. We already had that 129. If not, we add 127 to our unbiased exponent. And again, 129 is 128 plus 1. And we take out our fraction bits, or we extract those fraction bits and put those into the fraction field. So our sign bit is 0, our exponent is 129, and our fraction is 0.0011, and then a bunch of zeros. And then we can write this in hexadecimal as well. We're going to get 4, hex 4, 0, 9, 8, 0, 0, 0, 0. And so addition, as we can see, floating point addition actually took a lot more effort than unsigned binary or 2's complement addition.